Okay, let's go. Alpha beta. So alpha beta is really not, a lot of people are scared of alpha beta for no reason. So here's alpha beta. Again, they're just a bunch of triangles. What's to be scared of? It's just triangles. So here's a simple binary minimax tree. And here's some random values put in here. So let's see, this is max, this is min, this is max again. What's the minimax value of this node, Evan? 3. Yeah, because it's max's turn. All right, so 3 percolates back up this edge. Right? 3, that's the minimax value. Goes back up that edge. Now, what about this node here? Who hasn't talked yet? Jen. The minimax, exactly. 5. So 5 goes up there. The minimax value coming up this edge, I don't know. Who hasn't talked yet? Joe. 3. Right. Now, what if instead of having a 5 here, I had a 15? The minimax value of this node would now be 15. This edge still be 3, right? Everyone see that? By the time we're here in the tree evaluating this max node, we know that there's a min above us on the path from the root. There's a min controlling our destiny that has an option of 3. So by the time I see that this is 4, I know this is a max node, right? So this max node is going to cost at least 4. I can already give up. Because I know min is going to take the 3. This is going to be at least 4, and min has a 3. So don't even bother evaluating this node. It has no influence on the outcome. Adam.
It's assuming they're sorted.
Nope, it's not assuming anything. I happen to have looked at them in this order, but I could have looked at them in order 3, 2, 15, 4. Then I would, if I looked at 3 and then 2, then I'd say the max was 3. And then I come over here, I'd hit the 15, and I'd say, whoa, 15 is greater than 3. Min has a 3 available to it. This is going to be at least 15. Therefore, I know we're never going to get here in play, because min is going to take the 3. Has nothing to do with the sorted order. So that we can short circuit the search right here. We can prune this part of the tree. Now there's only one node there, but we can prune it away. We don't have to evaluate it. Lee?
I was going to say, so you're pruning, and then you said that.
Exactly. Pruning. Clipping away part of the tree. Technical term. Okay, so let's go over this part of the tree here. So here are 1 and 2, so the value of this part of the tree right here, Kendall, what's the minimax value of this node right here? 2. Exactly. Now, what do I know at this point? I know that this is a min node. It's going to be 2 or less. Above me, there's a max node where max has the option of a 3. So this is going to be 2 or less. Is max ever going to choose to come this way? No, because max has a guaranteed 3 the other way. So this entire portion of the tree here gets pruned away. Nice! Okay, so that's alpha beta pruning. It's keeping track of what options do min and max have higher in the tree along the path to whatever node we're at? Okay? That's the basis of alpha-beta pruning. It's getting rid of things that aren't going to make any difference in the final outcome. So the minimax value of the root is unchanged. Okay? We're computing exactly, perfectly, optimally wonderful minimax values, just faster by ignoring parts of the tree. Frank?
So if we had done a right-left traversal, it wouldn't have helped at all?
So what are these? Well, I don't know what these are going to be. 3 and 4, maybe? All right, let's traverse the tree backwards. For Frank, I'll do it in a number. I'll do it in green. Okay, so this is max. So this is going to be 4, and then here this is going to be 2, and so this is min node, so that's going to be 2. And then I come over here and I look at this 4. I don't think I can do any pruning right away at the 4 if I hit this 4. So then I look at the 15, and now I know that this is 15, and I still can't do any pruning. So I come over here, and I get the 2. So now I know this is going to be at least 2, and min has a 15 available, so the 2 might still work. And I can't prune this whole thing here because, yeah, so I have to evaluate the whole tree. So minimax is sensitive to node ordering. That's a really good point that you bring up. It does depend on the order in which you evaluate nodes. It also makes trying to analyze theoretically what performance advantage minimax gives you really tough. So the first person to analyze minimax, I think, was Donald Knuth, who is like superstar computer science guy.
Once you get to 2, can you stop? Because you know it's at best equal to the 2 on the other side?
This is a 15. If this is a 25, then this is going to be worth 15, and max is going to take it. Okay, so everyone understand the intuition behind minimax now. So now the question is, okay, how do we write down that algorithm? And luckily, someone else has done it for us. So this is where it's good to accept the institutionalized wisdom of those who came before. These numbers about what min and max can do are called alpha and beta. So alpha is the best outcome max can force at a previous decision along this path, and beta is the best outcome min can force. And the thing to realize about minimax values is that they only go down the tree. Minimax values go up the tree, right? Just like we always do minimax backups up the tree. But alpha beta values just come down because they're all about, the minimax values are all about what has happened previously higher up in the tree. So minimax values come down and alpha beta values come down and minimax values go up. Okay, so the code is like so short. You're like, oh, this is easy. But if you ever try and actually implement this, I guarantee you this is like course project worthy. So we start at a max node, and alpha and beta are initialized to their respective infinities. I guess alpha is supposed to be max's best, so it's negative infinity, and beta is infinity. Is that right? Yeah, exactly. Wow, I can't believe I was right. So we look and we see, gee, are we at our depth cutoff yet? If so, we return the static evaluation of the node. Otherwise, we're going to go deeper. So we go look and we say, all right, we have some alpha and beta passed into us. If this is a max node, alpha can go up as we look at the different children. Like the best that max can do along this at this point could go up potentially. So we're going to set alpha to the max of its current value and the minimax value we get from the child. So our child is going to be a min node, so we pass alpha and beta down. And this is the current alpha that's being updated. Now, if we're guaranteed that min higher up in the tree has something lower than what we could get at this node, then we know that this node is completely irrelevant and we can bail out and return. Otherwise, we just go along and we return the max value we can get. This is the new minimax value. We pass back up. So let's see this. Let's see if I can successfully run this in a pseudo in an example in class without my notes. Okay. So let's just do that same example with the alpha and beta values. And we're going to end perfectly on time. So right here, as we head down, alpha is negative infinity and beta is infinity as we go down. And right here, alpha is still negative infinity and beta is still infinity. And we hit this max node. And then we hit a 2. And so now we update alpha, right? Because this is a max node. So alpha is now equal to 2. Beta is infinity, so we don't bail out. Right? Because we have to wait till beta goes under alpha. Now we do the 3. We didn't hit anything, so 3 is now passed back up. 3 is the minimax value that goes up. Now here we are at a min node, and that means we're updating the pseudocode for min is just alpha, beta are reversed. We're updating beta to be the min of its current value and whatever value we get from the kids. And we prune when beta goes below whatever our max is guaranteed to get. So pseudocode is just the reverse. So you can tell this is like exactly the thing I'm going to ask on the first exam. So here now we're updating beta. Beta is now 3. We come down. And so now we come down with alpha is positive infinity and beta is 3. Does everyone understand that? Right here at this point, when I enter this max node, alpha and beta are percolated down, never up. So the fact that alpha was once 2 down in this node is completely irrelevant, because that's not alpha and beta values are not inherited, in this roundabout way. They're only inherited down. So as of here, alpha equals negative infinity. Now the first thing we do is visit a node of cost 4, and it's a max node, so we're updating alpha. So alpha equals 4 at this point. And now, beta is 3. Alpha is 4. And that should trigger pruning. Am I right in the pseudocode when we're doing max here? Max. Alpha is 4. Now we just updated alpha to be 4, and beta is 3. So we return, we prune. Wow, the pseudocode is working! Fantastic. So we're going to prune, just like we said we should, prune that node. And we will pass up 4, but it will be ignored. And the value of this min node is going to be 3. Everyone follow along there? It's a little hairy. It's a little hairy. Dan is saying that he doesn't follow along. Where did I lose you?
Beta becoming 3.
Right here. Okay, so in the loop for min, where we're going through each child, we update the local beta. Okay, that's this step right here.
Every local beta?
No, just the current one for this node.
Okay.
There's a separate. Yeah, alpha and beta are not like global variables. They're not global. They're local. They're passed down, and each recursive call has its own copies. Which makes perfect sense, because when I'm here at this node, alpha is the best move for max at any point up in this tree here. The fact that max once had a move down here that was good is completely irrelevant.
Can you go over kind of quickly the recursion calls, like how it gets passed down and then where the beta gets set?
So alpha and beta always go down and minimax values go up. Minimax values always go up because alpha beta is still computing correct minimax values. So the only complication with alpha beta is we have these alpha and beta values coming down. And they start off coming down here as negative infinity and infinity. Then here they're still negative infinity, infinity. Now here, inside this max call, right, we're called with parameters alpha and beta that are negative infinity, infinity. We're a max node, so we update alpha. Once we visit our first child, our own local alpha becomes 2. Then we look at this guy. I guess if you want to be technically precise, our local alpha becomes 3 here because we're a max node. And then we return 3 as our minimax value. But here in this min call, we still have our local alpha and beta that are negative infinity and infinity. Because what comes back from this call is just the minimax value, not alpha and beta values. Now it's true that we are using alpha, that the alpha value, the local alpha value does happen to be the minimax value. But when this returns back to this call, we're not modifying we're not modifying the local alpha value, for example. We're just computing the minimax value. So just always remember the minimax values go up and alpha beta values come down. In a min node, we're modifying beta. In a max node, we're modifying alpha. So here, when we get to here, alpha is still negative infinity for this inside this min node. And all that's being modified is the beta value. So here, beta is still greater than alpha, so we have to do our recursive call. We can't exit early. We come down, alpha is still negative infinity. Then alpha gets updated to 4. Beta is 3. Beta is below alpha. We can prune. So up here at this top max node, what gets set before we look at the next child? Exactly. Alpha equals 3. Exactly. So when we come down into this first child here, we're coming down with alpha equals 3, beta equals infinity. Then we're going to look here. This is a max node, so we're updating alpha. Alpha is always going up, so alpha is still equal to 3. 2. We pass back 2 up here. This is a min node. Beta is getting updated. Beta equals 2. Oh my God, beta is less than alpha. Prune. So it all works out perfectly. So that's alpha beta pruning. Now, granted, I think if I took away all your notes and made you do it now, we'd probably make a few mistakes. But do people get the idea and see how the pseudocode probably has something to do with the intuition? And then we'll do another example of recitation on Friday, maybe. Okay, so that's alpha beta pruning. Just, a couple of lines of code. We do all this pruning. What's the average speed up, do you want to guess? Oh, wow. How did you guess? You know how to read. Brilliant. Yeah. So now, how big of a deal is that? It's just a little 2. But it's in the frickin' exponent, right? D, we can go twice as deep in the same amount of time. Instead of going to depth 10, we can go to depth 20. So this is a big deal. Big deal. Alpha, beta, and this is all average case. We're totally not going to prove it, so we're just going to take it on faith. But it It lets you go about twice as deep, and it's incredibly effective in practice. And it's just a few extra lines of code. So every game program does alpha beta pruning. So it's really important to know about. Now you know about it. So now you know the basics of adversarial search. Let's see if there's anything else worth mentioning. Here's a nice practice tree. If you're like studying for some exam and you're like, oh, he keeps talking about putting that on the exam, you might want to practice percolating your alpha and beta values and make sure you get exactly these same prunes that are written in the tree. Yeah, let's see. I put it on the course webpage. Where are the links? Where are the links? Here we go. Required reading. It's a great comic. Here we go. So this is very recent. This actually is incredibly accurate. So this is true. So tic-tac-toe. I don't even remember what NIM is. It's some really stupid game. Solved for all possible positions. Right, so we know exactly what to do in any circumstance. Solve for the starting position, checkers. Very recent result. It took Jonathan Schaefer, he was running his program for like 20 years.
What?
Yeah.
He like put it on new hardware,
Yeah. And in fact, at one point, he lost like half his work. But that was like 7 years in. He lost half his work. But it took him only 9 months to recreate it because computers had gotten so much faster. Plus his algorithms had gotten better too. So by the end, by the last few years, he was running on 40 different machines. He has an enormous database, so he got to the point where his files were so large that every time he copied a file, he had to checksum it because there was a non-negligible chance that the bit error rate on the hard disk had erroneously set a bit. Hard disks are only guaranteed to accurately read something like they have an error rate of 1 in 10 to the 15. Yeah, so if you're copying large amounts,
Internet communications is like 10 to the 7.
So he was like, he had to write his own file copy program that did fancy checksumming because like he was running on imperfect hardware and he had such large files. Yeah, there are a lot of positions in checkers. It's a big game. And it's now solved. Computers can beat top humans. I have not been able to find a YouTube video for the UIUC robot that plays beer pong, but apparently it exists. This chess is kind of funny. So 1996, first win by computer against top human. 2005, last win by human against top computer. So chess is definitely in the computer category now. Jeopardy, we just had this very narrow win by Watson. Go, the 9x9 version of Go, computer has successfully played against like master's level humans, not like the very best humans, but like quite competent humans, and done okay. Full Go is still beyond computers. So anyway, so there's been a lot of progress in games research. And I think that's...
I think Mao would be a really interesting one to try to...
I don't even know what that is. A lot of these I don't actually know what any of the three of these are. I assume that's something from...
Calvin and Hobbes.
Calvin and Hobbes, yeah. It's like you jump into a swimming pool.
You make up the rules as you play.
Oh, okay, great. Well, there you go. Actually, this would make a great end of lecture question. There is a general game playing competition now, where you bring your program and you get the rules, and they're machine readable, and the program has to figure. The computer gets like 3 hours to do whatever pre-processing on the rules it wants, and then it has to start playing. It's called the General Game Playing Competition. Because everyone was like, oh, chess, Deep Blue just knows how to play chess. It doesn't realize it's playing chess. It's just playing chess. So, okay, let's build a system that can play any game. And they usually suck, but they are playing. And so they've entered a human in the general game playing competition. And depending on the game, the human can get beaten.